All right. Hi, everyone. How's it going? Okay. I'm worried all of a sudden that I smell bad or something because there's like a empty seats like right. Nobody wants to say it. I don't know. Is it true? Okay. He's like, oh. Okay. So let's see. I just want to continue where we left off and get to these concepts of work and circulation. And like I said, I should look at these slides. Well, we're going to get to these slides in a minute, but yeah. So let me remind you where we left off. So we were talking about, these line integrals where you integrate along a path. So line integrals, sometimes they're called path integrals. And we talked about this idea that like, okay, here's your path. So it's oriented in a certain direction. And what I want to think about is that's living in a vector field. So let me just draw some vector field here. So let me just draw some sort of like constant vector field. Just kind of assume we're living in some vector field, right? Just drawing a constant vector field. So oriented path C, oriented curve. Where oriented just means we've given it a direction. Vector field F. And of course, that's the idea that every point there's a vector coming out of it, right? And we have this idea of the line integral. So we want to view work, the physics concept of work, as the integral sort of, what we're going to do, I wasn't really doing this on Monday, but we really just write C, meaning sort of along, maybe I'll just write along C. Integral along C of, we talked about how to sort of integrate a function along a path last time. That's what we spent most of the class talking about, is how to make sense of that, right? We had like the Riemann sum concept of like what it would mean. So the component of F along C, that's the function we want to integrate, right? It's basically force times distance. It's like, remember, you should think of an integral as like a sum of a bunch of tiny things. And the tiny things we're doing is adding up the work along each little tiny segment of the path, right? So in some sense, I'm saying just like, you should think of this as add up force times distance along tiny segments of C. I could write the Riemann sum again, but that's kind of what we end up doing, right? This is like force times distance. But the force only cares about the component along the path, right? That's kind of what we were talking about with the ramp last time. If you remember from Monday's class, we were talking about like pushing a block up a ramp as opposed to lifting it directly. So like, if we're at a point on the path, like say, let me just make this a little more stark with a specific point. Like if we're like here, say, there's your force vector, but we also have the direction of the path at this point, right? And we just want, so this is like tangent, this is like your force field vector. This is like your tangent vector to the path. And what we really just want is sort of the component maybe I should draw this bigger. Like, let me just draw this bigger down here. So here's your F. Here's your tangent vector to C. And so the component of F along C is this right here, right? That's the component of F along C. Does that make sense what I'm saying? Like when you apply a force to an object moving in a certain path, it's just the component of along the path. The component, particularly the path, is kind of lost. The component along the path is what is kept. And then, okay, so I claim that this looks kind of complicated, like how do we ever compute something like this? But there's a kind of nice, there's some nice stuff here. If we actually start thinking about what we started doing last time, where we looked at what the dr means, right? The dr represents a tiny piece of the path, represents a length of a tiny piece of C. But then we said, well, let's parameterize. And let me do this sort of abstractly, and then we'll do examples, and we'll see how this works. But parameterize C by one of these R of T, where, you know, one of these parametric equations, vector equations. What we said last time is that dr, well, we could write dr dt, because I want to sort of get towards this dr thing, how we would express that. So dr dt is r prime of t. We talked about that for the circle example, right? Going around the circle. And then you can sort of do this thing where you're like, okay, well, dr then is, we could think of it this way, like we're doing a u substitution, because that's how we're going to actually evaluate the integral, is sort of substituting the parameterization in. I just move the dt over like that, right? And then dr, so this represents the actual vector of a tiny piece of the path, right? Like a little, like if you broke that whole path into a bunch of tiny little vectors, that's kind of what you're imagining the dr is. Not the length of the tiny vector, but the actual, like, tiny piece of the, like a vector representing a tiny piece. Representing a tiny, I'm just gonna keep writing tiny piece of, because this is honestly how I think of integrals. And then the actual length then is just the magnitude. So dr, which I was writing without the vector above it, is like the magnitude of this, which is just the magnitude of the tangent vector times dt, right? So I'm just trying to write down, I'm trying to get at how we could use the parameterization to actually get at like how we would actually integrate. Question, yeah, Milana. I guess it's like you're forcing it to go along the path. And yeah, we're going to talk about some of like qualitatively how to think about this. But you're kind of you're trying to force this along the path, and it's like you're going to, it's like think of gravity, right? When I'm going upstairs, like if I want to follow, I can follow a specific path, but then sometimes I'm going against gravity, sometimes I'm going with gravity. And so when you're going with gravity, well, we actually think of the work of the vector field on the particle or on the person or whatever. Like I think of a particle following this path. Yeah, I really should say, I guess I should say like, we're going to imagine a particle traveling along the path. And then the work is like how much work the vector field does. So if I'm going downstairs, the gravitational field is doing positive work on me. If I'm going upstairs, the gravitational work is doing negative work on me. If the force, yeah, so it's it's gonna have a lot to do with like, to what extent the path is going with the field or against the field. And again, I'll definitely talk about that very soon. But sorry, it's a good question because we want to think about this qualitatively. But let me, the nice thing is we're going to see something nice in the math in a second, and then we can go to the qualitative stuff. Okay, the other thing I should have said here is, if we think of this, let's pull this back down for a second. How do I measure the component? We've done this before, right? If this is the angle, and then this is the length of that, then what is the component actually in terms of these two quantities? Yeah, we just multiply by cosine, right, to get that. So really one thing we could do is we could see this as like magnitude of f times cosine of theta, right there. And now we have a formula for this too, going all the way down here. So if I plug those both in, let me just plug those both in, because then you're going to see, and it's going to be natural. You're going to see what's going to happen. Plugging in work is the integral along C of the magnitude of f cosine theta times the magnitude of r prime of t dt. Right, that looks like a lot maybe, but I'm just plugging in the expressions we found up there, right? And now something should maybe jump out at you when you see something like this. I mean, f is that green vector up there. R prime really is that yellow vector up there, right? Because it is tangent to, we said this is tangent to the path. So when I see something like magnitude of f times magnitude of r prime times the angle between them, what do you think? Dot product, dot product, dot product. Yeah. So actually, this is really f dotted with r prime. And all of a sudden, this becomes interesting because we don't have to know theta all the time. We don't have to calculate magnitudes directly. We can literally just dot the vector field with the tangent, which makes sense because that's kind of, this is really how we thought about projecting, about how we think about taking components. We actually think about dot producting. So that's exciting. So actually the work, now we have an actual formula. So work is the integral, well, I'll just still say C. We're really gonna do it from little a to little b if we do this. But it's f dot r prime of t dt. And actually, r prime of t dt is actually this dr right here that we were calling it. So then actually the way people write this is the integral along C f dot dr. So this is, I mean, this formula they just sort of give you straight away in the book, but I feel like you kind of have to derive all the stuff behind it, like where this actually comes from. So that's kind of the way when we look at the book and when I write these things down, this is what we look at as like a work integral. If we're going to compute it, we actually move it over to here with the parameterization and plug everything in. And we'll do that in a moment. But that's the conceptual idea of like what the work integral is. Okay. And so now, if I go to the screen here, let's just look at some of these. So this is some vector field that's circulating around the origin, right? It's going around the origin. It's getting longer as you go farther away from the origin. And these are different paths, which you're sort of, you know. And it's what I'm saying here is like, if you wanted to follow, remember about I guess, yeah. So if you think about like the integral along C1 or C2 or C3, the path is following the vector field, right? So the dot product of at each point is going to be positive because remember, it depends on the cosine of the angle. Positive dot product means pointing the same way. Negative dot product means kind of pointing the opposite way because it's a greater than 90-degree angle. Right, so those are the things you have to keep in mind in your head. So really what's the question is, what is the sign of all of these? Are these which ones are positive and which ones are negative? Ooh, somebody want to guess? If you think about following the field versus going against the field. Following should be positive, and going against should be negative, right? Because you just think about these dot products. If they're in the same direction, then it's the cosine's like 0. But if they're in opposite directions, the cosine's -1. So they're going against each other. And so, wait, can I do this? I think I just have this way, yeah. Yeah, so the integral along each of these, this is on the handouts page, but also if you want to just sort of like roughly sketch. The integral along each of these first 3 is positive. The integral along the 4th one is negative. Make sense? Yeah, if you're definitely just like, if you're really following the force field, then you can really tell quickly whether it's positive or negative. Okay, so, this is interesting. If you actually go around a closed path, then notice you can get a non-zero value. Sort of interesting. And here this would be positive. So this is called circulation. Circulation is the line integral around a closed loop. I should write that down. I'm just gonna, so we have work, which is the line integral along a path. But then this term circulation is used for the line integral around a closed loop. And well, okay, yeah, we'll talk about what that means, in a few minutes, and some examples. But circulation, sort of a line integral, CF dot dr, where C is a closed loop. In some books, I don't think in our book, but in some books, or some places, they actually put a little circle on the integral like that. You might have seen. Oh, sorry, yeah. Yeah, it can be any close. It doesn't have to. Oh. Okay. Yeah, it doesn't have to be. It's a circle, I guess, in that picture, but we'll see some examples in a second where it's a closed loop. So some books, they actually put a circle around the integral. Stop the share first quickly so people can see that. Yeah, some books will actually, and if you've seen like Maxwell's equations, sometimes they're on t-shirts and you see an integral with a closed loop. Yeah, actually, I'm sort of curious now. Let me share the whole screen. Maxwell's equations for electromagnetism. Maxwell's Silver Hammer is a song by the Beatles. Images. Well, this is the differential form. Yeah, but you'll see stuff like this. Oh, that wasn't helpful. Yeah, like these integrals. This is this is an integral over a closed surface. But yeah, so you'll see this kind of thing. And then, yeah, we'll talk about some of this later. But anyways, so that stuff comes up. Right. So it comes up a lot of applications, a lot of physics applications. Okay, so that's called the circulation. So here's an example. If I do some sort of like loop here, let's say counterclockwise, is the line integral going to be positive, negative, or 0? Do people agree with that? Positive? Yeah, it's interesting. Like if you make a rectangle, so that's a loop, that's not a circle. There you go. It definitely follows the field there. It's actually perpendicular to the field here, so the work is 0. That's like walking back and forth on the same floor on a gravitational field. And then you follow that way. So this actually has positive circulation. Actually, yeah, like I should say that the convention is to orient C counterclockwise. Like the way that, like our convention is sort of a we have all these conventions that are really counterclockwise, right? Where we like angles increase in a counterclockwise direction. And so we traverse loops in counterclockwise directions. And so this is going counterclockwise. So this has some positive circulation. What about this one? If I make some loop. Can you get non-zero, Leo? 0? You say positive? Some people say positive. Yeah. As long as it's closed, a closed loop. Yeah, and it could be anywhere. I mean, we're kind of trying to just decide. There's actually a general question of whether a vector field has positive circulation, negative circulation, or 0 circulation. And it can change depending on where you are in the vector field, but some vector fields are kind of always positive or always negative or always 0. So if I just have some sort, I mean, it's easiest to do like kind of rectangles and stuff here, right? So let's vote. How many people think it's positive? How many people think it's 0? How many people think it's negative? Okay. Yeah, it's 0. I guess if you kind of it looks called circulation free sometimes. Like if you draw some paths here, like this would be negative, but then that would be positive. But then up here is kind of negative, canceling out this positive, right? These are perpendicular to the field. This is sort of just like, this is very qualitative, right? But this is sort of a way to look at these things and see. Yeah, Caleb. Yeah, so you're asking, just for people who can't hear, that this is what's the difference between these two fields? Yeah, I mean, it's sort of an interesting thing. It's like you're saying this side's positive and like this side's positive. This is in the positive x direction. Like that's in the positive y direction. This is in the negative x direction. This is in the negative y direction. I guess the thing is, like, if you look at these paths down here, if you have a closed loop, sort of every piece that you have going one direction, there should be another piece going the opposite direction, sort of. And here, yeah, because if you turn your head 90 degrees to the right, it's a little different from this picture, right? Because they're all going up here, and they're all going down here. So this actually has, and another thing you can do is think about a particle in here, right? If you dropped a particle in here, well, it would get pushed that way if you're over here, but over here it'd get pushed that way. And those are kind of opposite ways. It's kind of, you get like it's almost like throwing a curveball where you get like a spin effect, right? Like on the different forces on each side. Yeah. Right here, right? Yeah, like it's definitely subtle, and it's kind of, and there's some problems on the homework about like actually looking at these and deciding if the circulation is, or if the line angle is positive, negative, or 0, or if the circulation is possible. So okay, that's an interesting sort of qualitative way to look at these things. is you're just sort of trying, it's really just asking, you're basically, your line integral is positive if it's going more with the vector field than against. If the path is going more with the vector field than against, and the line integral is negative if it's going more against the vector field than with. And it's 0 if they cancel out, or if you're going perpendicular to the vectors all the time, or something like that. Okay, okay. We actually want to compute some line integrals. So let's actually, here, this is a handout, but let's do some of it together. Actually, I want to write all these down, but let me do like just an example. So, yeah. Okay, so let this, I'll leave this on screen. If you're watching on Zoom, you can pull up this handout. But let's talk about how do we actually, we actually want to compute these things. So that was qualitative, what we were just looking at with the images, but how do we actually compute a line integral? Compute a line integral. So here's an example. Yeah, I have you look at some different ones. We're gonna do group work at some point soon, but here's a vector field. Let me just do this F1, which is 2x plus yi plus xj. And let's do one of these paths. So these are actually 3 different paths from 0, 0 to 10, 10. Let's just do the first one, and then we can think about whether we want to do another one just to see. So C1 is a straight line path from 0, 0 to 10, 10. So that's just something like this, right? Path like that. We can parameterize this. Oh yeah, so compute, right. So we want to compute the integral, the work integral, the line integral f1.dr over C1. So we can parameterize this a couple different ways. So a good parameterization of this, it's just x equals y, right? So you can just use x equals t and y equals t. Maybe I'll just write it this way. So you could also do the way we did it on like the homework assignment, which is you take the difference, use that as a vector. So you could actually use 10t instead of t, so going from t equals 0 to 1. Or you can go t goes from 0 to 10, either way. So this one is actually t goes from 0 to 10. And if we wanted to write that in sort of this vector form, it's just like this, right? Ti plus tj. And it's going to be useful to know the derivative, the tangent vector. And actually, this is nice. T becomes 1 and in both times. And so actually, you get the vector pointing that way, which makes sense that that's tangent to the path, hopefully. If you didn't believe before that r prime was tangent, then hopefully believe it now. Okay, so then the integral has actually become not too bad to compute once you have the parameterization. Because we're just going to plug everything in now. We're going to plug in the parameterization, and we're going to end up doing this stuff down here. Let me stop the share, right? Yeah. Let me leave these on the board just for a minute. So we're going to integrate along C1 f1.dr. And we're really going to do that as the integral of f1 of x comma y dotted with r prime of t dt. But let's think about what I actually mean here. So this is along the path, right? So actually, let's just write this out a little bit more carefully. This thing right here, we said is 2x plus y I plus xj, but x equals t and y equals t, right? So this actually equals 2t plus t I plus tj. So it's 3t I plus tj. So we have, this is really basically the vector field along the path. At any point in the path, this would be the arrow of the vector field along that path. Does that make sense? If you actually just want to know what the arrow is at each point. And then we're going to dot that with r prime. So, but let me just write it out. So really what we're doing is we're doing an integral of 3ti plus tj dotted with I plus j, not the tangent vector, dt, and we're integrating from 0 to 10 because we've turned everything in terms of t now. And that's what we decided the parameterization was. Does that make sense? You basically only care about the vector field at points on the path. And that's what we're doing here. We're just plugging it in the path. Yeah. And now this is something that we can integrate pretty easily, right? Because we just get, if we dot these together, we just get 3t plus t. Right, we just multiply the x components and multiply the y components and add them. So I think that just becomes the integral 4t dt, which is good. We should get rid of the vectors. And so we get 2t squared 10, which is 200. Good, that's what I remember the answer being. 200, whatever we're doing here. Not really clear. But yeah. Let me just share screen again. I was going to just show you the vector field. So user defined field. Hello. So if I put 2x plus y here, I think I have to use asterisks for multiplication and x. Oh, hello. Field vectors. Yeah, actually having less is better. So that's something, this is the origin. Yeah, notice if you just got to kind of go directly up and to the right, the vectors are a little more right than up. And you sort of see that here. If you plug in like a small positive values of t, like t is 1, you get over 3 up 1, t is 2, you get over 6 up 2. And so that's what you're doing. You just care about the vectors along the path. If I go over here, it changes because now, well, it's x and y is really, it's not on the path anymore, but you know, x is positive and y is negative, or x is negative and y is positive. This could be negative or positive, and then this is negative. So they all point to the left. Remember, this is just how to think about vector fields. Looks like they're all sort of pointing to the left. I mean, no, sorry, all pointing down, sorry. X is negative, so xj is pointing down. So in the second quadrant, they're all pointing down. And then whether they're pointing left or right depends on the relationship between x and y. But anyways, that's just to make sure you're kind of. So doesn't it have, wait. Oh yeah, well, I think this is just a circulation. Oh, circulation is 0. That's interesting. See, here's more examples of the circulation thing. Like, it's kind of showing you actually. Oh yeah, so it's, well, wait, it's going counterclockwise, right? So like Here it's going against the field, that's why it's red. I don't know if you can see that. Here it's going with the field, and here it's going a little bit with the field. Here it's almost zero, so there's not much going on. But somehow they're claiming if you did it around a closed loop, you would get, if you integrated around a closed loop, you'd get zero. Okay. So we're good, we know how to compute a line integral. Let's go back to this. So yeah, so like this is basically the steps of this is sort of like how you do this, right? So you write down a parameterization for the path. You write down what you get when you plug the parameterization into the path. Yeah, I mean, there's a sense in which really what I should write here is f of r of t. Let me just do that. So because we really are plugging in, you'll see it written this way in the book. You really are plugging in the path. It's almost like f of u du. It's sort of like something like that. So yeah, okay. Do you guys want to try this yourselves for 15 minutes? So yeah, so you can do, I wanted you to do this for two other paths. Like one is like going just a horizontal segment and then a vertical segment. So you actually have to do that as a sum of two integrals. You have to parameterize each piece of the path. So the three different paths from 0, 0 to 10, 10, right? The first one was just the straight line path. The second one is like over and then up. And then the third one follows some parabola. But you can tell it goes through 10, 10. I'm just kidding. It's just interesting to see what happens when you try this with three different paths. Okay. So let's just do this. Let's get up, get into groups, go to the boards, try to compute the one along C2 and along C3 and see what you get. And then if you have time, you can go to the other vector field and compute integrals there. We just want to practice some. It's basically what the homework is for Friday too, is just practicing some of these line integrals. So thank you, yes. And if you're on Zoom, just pull the handout up. Here, let me share. Yeah, just pull up the handout and then try to compute. We basically did we did 1 through A through C. Yeah, I'll just focus on F1 today, and then maybe Friday in class you can do F2. So do F1 along each of the three different paths. We did the first path. Yeah, try to write the parameterizations down first. I'll try to watch the Zoom. I mean, watch the chat on the Zoom, and then I'll put stuff on the board. Maybe before the end of class, what other students got, but I'll watch the chat if you guys have questions. But I'll mute myself so you don't hear me just going around the room talking to people. Okay. Myself. All right, yeah, please raise your boards, straighten up the chairs, and we'll continue from here on Friday. All right, everyone, and then now you should be able to do the homework also for Friday. So, yeah, take care. See you. Yep. This was the first. All right, I'll stop the recording there, but you might pause and look at this. This was, yep, take care. This is part of the handout, so we'll continue from there on Friday.